Now we are going to solve for plume velocity. We have already seen how the volume flux, reduced gravity, and buoyancy flux change with height, and we now model for how the plume velocity change with height. Okay, so there are two different ways to model for plume velocity. So here we will not start with the original governing equation, so we are not going to use Navier-Stokes equation. Rather, we are going to use a simplistic approach, and that will also be filled with some assumptions. So there are two primary ways to consider plume velocity. So let's assume that this is the plume which is rising up, right? That is in case okay, and we'll consider one more case. So and we are assuming that here there is q naught g prime naught, which basically gives us b naught, and here also we have q naught g prime naught, which gives us b naught. Okay, so when plumes comes in, obviously there is some velocity, and also even if there is not a very small initial velocity, because of the buoyancy difference, because of the density differences, it creates velocity, and higher the density difference, there will be higher velocity, right? So what happens is, as we go, if we plot velocity profile inside the plume, we can do it in two different ways. So we assume that ambient velocity is constant, that is 0. So let's say that is w is the vertical velocity, and for ambient it's 0. But inside the plume, this is the velocity. Okay, this is a Gaussian profile. Here again, if you go further up, we assume that there is this velocity profile. If we go further up, this is the velocity profile. So we assume that w is 0, that is the vertical velocity of the ambient. So that is simply the vertical velocity, and as we go outside the plume, w is 0, that is the ambient, and inside the plume there is this velocity profile, right? So what you see here in the curve is the velocity profile, and it has maximum value at the center line of the plume, and as you go away from the center line, the velocity decreases. So this is an assumption, first assumption, where here we assume the velocity to be following a Gaussian profile. Okay, where it's 0 or tends to 0 away from the plume, and it comes, increases at the center, and then comes down. Okay, and other profile is known as top hat profile, where we assume that velocity is constant within the plume at a particular height. So we will assume that this is w, which is 0 outside, but there is this constant velocity within the plume. Likewise, here we assume that w is 0 outside, but inside the plume there is this which is little smaller than the previous velocity. Here again we have this w equal to 0, and then we have this velocity. Okay, so what we are assuming here is the velocity within the plume at that particular elevation z is constant. Okay, but as we go up, it is decreasing. Okay, so here we can assume that this is elevation is z1, here it is z2, here it is z3. So as we go up, the velocity is decreasing, but within that that elevation, the velocity inside the plume is constant for a top hat profile, whereas Gaussian profile, velocity within the plume, even for that z, is changing. Okay, so in the current case, we will assume Gaussian profile and we'll try to find a solution for the Gaussian profile. In what we see here, or what we are trying to model, is for, we consider the plume to be fully developed such that it has achieved the steady state condition. Okay, so we are assuming or considering the plume to be fully developed, and by that we mean that when we start injecting, plume starts developing, but if you continue injecting dense fluid for a long time, the plume will have risen up already, and now the differences we see only at the top, at the other end of the plume, but here the plume profile is fully developed and it's not going to change, it will remain same with time. Okay, so that is the steady state plume. So, considering that, we are going to derive a solution for a Gaussian profile plume, where the velocity is changing in a Gaussian pattern within the plume. Okay. So once again, this is the plume we are talking about, where we have okay, so this is Z1, Z2, Z3. Here W is 0, W is 0 outside, W is 0. And so this part we assume W max 1. This one we'll call W max 2, and till here we'll call W max 3. Okay, so what we see here is, as we increase, as Z3 is greater than Z2 is greater than Z1, right, where from here we measure Z, your W max 3 is actually smaller than W max 2 is smaller than W max 1. Okay, where what is W? W is the vertical velocity of the plume, and W max is the maximum velocity of the plume at the center line, right? So at the center middle of the plume, the velocity is maximum, but as you go away from the center line, velocity obviously decreases, right? And as we reach the boundary of the plume and the ambient air, velocity has become equal to 0. Okay, so as we go up, your W max itself is decreasing, right? But the profile, the trend we see remains same. Okay, and that is why if you want to plot W by W max, okay, with R by radius, let's say we also define okay, so this is your R1, this is your R2, this is your R3, so that is the plume radius, which is also increasing. So if you find a profile of W by W max against R by R max, it will look something like this. Okay, where this is 1, and this is also 1. This is 0 0. Okay, so this profile that you see will be applicable for all z value. Okay, z1, z2, z3. So if you divide your w by w max, where w is changing with radius and also z, and plot that with r by capital R, then you will get the same profile. Okay, where w here is function of r and z both, and r here is the radial axis and capital R is the plume radius. Okay, so what we get here is a similar profile, a same profile at different locations, and that is why this profile is called self similar, which is qualitatively same at all vertical locations. Okay, so basically we are trying to derive a self similar solution for this particular case. Okay, so what we are trying to do is we are trying to find this velocity profile w as a function of r and z. Okay, so as we already seen, w by w max, that remains same. Okay, if we try to define that as r by capital R, and we have seen that this is a Gaussian profile, so we can assume that, so w here is function of r and z. If we divide by w max, that must follow e to the power minus r square by capital R square. Okay, and this is equation for Gaussian profile. Okay, where for now, so this actually would give us w max as e to the power minus r square by capital R square. So this is the equation we want, right? So we want to find the velocity, vertical velocity of the plume at different r and z locations, and for that we must find w max first, right? Because small r is the radial location and capital R is the radius of the plume, so we must find w max, or we must define w max. Okay, so what is w max, or how do we find w max? So to find w max, we will use dimensional analysis. Okay, we will use dimensional analysis, and to be able to do that, let's start with considering what all parameters the plume is dependent on. So for analysis, length scale available with us are r and z. Okay, so that is radial axis and vertical axis, and other parameters, fluid parameters, we have our, let's say, viscosity and density. These are two fluid parameters, right? But remember that we are trying to find w max, where w max is a function of z only. Okay, so w max is only a function of z, but w max is not a function of R. Okay, and that is why if you want to find W max, R is irrelevant. Okay, for W max. Okay, so we are left with Z, and because we are already considering the fluid to be highly turbulent, the plume is highly turbulent, so the viscous effects are irrelevant, right? That is something we already discussed before this case, this particular point, right? If turbulent are highly turbulent in nature, and that's why viscous effects may be neglected, and because of that, in this formulation we will consider that mu is also irrelevant. Irrelevant for a turbulent plume. Okay, so now basically we are trying to balance inertia force only with the buoyancy force. So rho basically represents delta rho, which gives us G prime, and also Q, when you multiply we get B, right? B naught or B, which is buoyancy flux, where W is related to the inertia force. So we balance inertia force with buoyancy force for plumes. Okay, so we are basically balancing inertia force with buoyancy force, and we are neglecting the viscous force. Okay, viscous force in this case is neglected. All right, so now coming back to this particular analysis, dimensional analysis, we now know that this is of no use because R is irrelevant, right? And also mu is of no use because mu is irrelevant for turbulent plumes. And that is why now we are concerned only with rho and Z, where rho is equivalent of B, right? From rho we get buoyancy flux, as we have seen here. And that is why W max must be a function of Z and B. Okay, it should depend on Z and B because these are the only surviving parameters. All right, so now we will apply dimensional analysis here, which says that dimension of W max must be equal to the dimension of, let's say, Z to the power A and B to the power B. Okay, and we don't know yet what is A and B. One thing we know is that W max is the velocity, and that's why it must be meter per second, right? And that is why ZA and BB must be equal to meter per second, right? Because W max is velocity, and dimension of the left hand side must be equal to the dimension of the right hand side. Okay, and now the other thing we know is we already know the dimensions of Z and B. So Z is meter and B is meter to the power 4 second cube B, right? So if we go up where we define buoyancy flux, you will see that B is meter to the power 4, this one, right? It's meter to the power 4 per second cube. Okay, so using that we put that particular dimension here, right? So now if you want to find meter to the power a and b to the power 4 by s cube and overall power of b equivalent to b by m by s, or meter per second. In that case, what do we see here is, sorry, there is a mistake here, so this should be meter, right? So we see that meter is there both in the first bracket and second bracket, whereas second is only in the second bracket. So so equating this actually means that b must be equal to 1 by 3, so that it balances the second, and then that gives us m to the power a, m to the power 4b, where 1 by s 3 by 3 has been already taken care of, and here b should be equal to 1 by 3. Okay, so basically this cancels out. So what are we left with? M to the power a and plus 4 by 3, which must be equal to m to the power 1. So this actually means our a here is 1 minus 4 by 3, so that becomes minus 1 by 3. Okay, so that is a, and this actually means that your a is minus 1 by 3 and b is 1 by 3. That means your W max, which was defined here, should be b to the power 1 by 3 and z to the power a, where z is minus 1 by 3. So W max, and one more thing we need to consider is, in this bracket we are doing dimensional analysis. So this actually is same here, but now when we want to move from W max to this, to we remove the dimensional sign, we must use this proportionality sign, because we don't know the numerical values yet. Okay, so basically this equation is dimensionally consistent but not numerically, right? So that equation with the square bracket is dimensionally consistent, so they have the same dimension, but that not necessarily mean that their numerical values are also same. And to be able to convert that in numerically same form, we must use some sort of proportionality, and that actually will convert these into equal sign using that this is alpha z minus 1 by 3 b to the power 1 by 3. Okay, so in other words, W max is equal to alpha b to the power 1 by 3 z to the power 1 by 3. Okay, so here this is the equation we get, where alpha is this is a dimensionless constant to be determined experimentally. Okay, so alpha is a dimensionless constant, it does not have any dimension, and that is why the equation that we derive here from square bracket to this one is still consistent. Maybe more precisely, this equation is still consistent because alpha does not have any dimension, right? It is dimensionless, but it does have numerical value. So now when we convert this square bracket into this equal sign, then we need to use some numerical value of alpha so that this equation is dimensionally consistent. Okay, so this is the equation we get for W max. And now if you want to plot W max with Z, it will look something like this, right? So Z is the elevation and W max is this is the source value, right? So W max actually decreases with 1/3 power of Z. So basically, as you go up from the source, your W max, or that is the center line velocity, that slowly decreases, right? And that is something we already had seen here in this particular plot. Like the center line velocity is very high at the beginning, but as we go up slowly, that center line velocity decreases, right? And it decreasing with 1/3 power of height. Okay, where we are considering a Gaussian profile. Okay, so now having found W max, we can actually define the radius WR. So WRZ must be equal to alpha b 1 by 3 z 1 by 3 e to the power minus r square by capital R square. Okay, this is what we had defined, right? Yeah. So this is the equation we get for vertical velocity of the plume as a function of Rz, right? Where capital R, that's the radius of the plume, is still not defined. So we are going to define that soon. And beta is the buoyancy flux. So B is same as B naught is equal to the source buoyancy flux. Okay. Alpha is the constant to be determined. R is again to be defined soon. Okay, and RZ are the coordinates. Okay.